while. Airflow measurements, a little predominantly, we have a pretty strong line of dampers and louvers, but we have noticed the need for some airflow measurement equipment and some airflow measurement equipment tied to dampers, where there's an adjustable control damper that can be positioned by the building management system and based on, say, intake airflow requirements and things like that. Just to give a background on myself, been with Pottorff, I said, a little over 16 years, was a design engineer for the first 7 or so years, and have been a product manager since about the end of 2015. And predominantly, I deal with a lot of damper products, but be able to help with airflow measurement applications and configurations as well. So talking about airflow measurement systems and why they're needed. If you're not dealing with a dedicated outside air system where you've got an intake air system, you certainly don't want to have that intake air system running constantly throughout the day. You don't want to have to condition more air than you need to keep a certain level of indoor air quality. Now, that indoor air quality is something that's typically set up from ASHRAE 62.1 and 62.2 standards, where they're either looking at commercial or residential type buildings and figuring out the type of occupancy, the overall load, the overall number of occupants that are needed, how much CFM is needed, and they use that to calculate the recommended number of air changes per hour. And so you've got the number of occupants and trying to figure out that number of air changes per hour to those air ASHRAE standards. Now, in order to do that efficiently, you could size your system to where the fan is basically running for a set amount of time. You've got an ideal ventilation rate for that fan setting, and you've got the duct that is connected to that fan, and you can use that to kind of rudimentarily set up the overall CFM you expect based on the ideal amount of airflow through that fan operating at normal performance loads. Now you can certainly do it that way, where you just have the fan run for a certain amount of time, and then that fan either shuts down or the intake gets closed off and you're recirculating conditioned air at that point until you want to open up and get a new change of air for that. Or you can do it a little more accurately by being able to measure the amount of intake air rather than just relying on the standards for you could do your airflow measurements just with your area of your ductwork and your pretty much set point for your fan, and just kind of go off of that. Or you could, I'm getting a little bit of feedback too. I might can you mute yourself, Robin, for a second? And perfect. That might have stopped things, hopefully. Where now you could do it a little more accurately by actually measuring the amount of airflow that you're getting through that ductwork. So if you're actually measuring that airflow, you're going to be using some type of probe. And not only are you using some type of probe, it could be pressure differential, it could be thermal dispersion, but you want to have a pretty accurate airflow measurement for that. And there are different duct devices that have certain requirements that create turbulent air. So if you're at the outlet of a centrifugal fan, or if you're in between, say, different elbows or a certain distance away from certain elbows, there's going to be some guidelines as to where these more specific airflow measurement stations can be mounted. And the reason for that is the only way to get a decently accurate measurement is to have laminar airflow. So if you've got some duct device, whether it's a turning vane that or a turning elbow that may or may not have vanes to help smooth it out, or some other device, a reducer, a fan, T intersection, anything like that, there's going to be a recommendation, a generic recommendation for how far away those airflow measurement probes should be from those devices to get the best accuracy, or at least the prescribed accuracy from the different devices, as the pressure differential and thermal dispersion, which are two of the main devices, do act a little bit differently. And this is really just to improve overall indoor air quality. So, um, your building control system is going to be a little bit more advanced when you're being able to tie in these airflow measurement systems. And they're going to take a signal from those airflow measurement systems and go back to a pre-programmed set of controls, or something that may respond to certain pressures, whether there's certain limits for temperature or potentially CO2 sensors, or just overall flow that's calculated in. It can work all those ways. And at that predetermined level, it can either take in more intake air that will have to then be conditioned, or recirculate the building air. There are some certification bodies for airflow measurement stations, and those typically deal with the accuracy of those airflow measurement stations. There's going to be AMCA 611 for the standard for doing that. And it's going to be a little different than, say, the AMCA 511 or AMCA 500 type settings, because it's not really geared around damper performance. It's really geared around the accuracy of the airflow measurement. So it works a little bit differently. The sizes aren't quite the same. It's really, you can test what sizes you want. Now, the sizes that you test will cover a certain area. It's kind of like UL rated, fire rated dampers. There's going to be a limit to what you can test. And you can certainly build airflow measuring probes and stations that are bigger than what standard AMCA 500 ductwork can be set up for. So you really are only testing representation of the area that you're covering with this unit. So there's going to be a maximum allowable size, and you can certainly provide units above those sizes, but the accuracy would only account for those sizes. Now, typically, there's going to be some note in someone's submittal for AMCA that will specify that if they haven't tested to a size that will cover them for their individual sections that they're selling. Now, talking about that, there's a couple of different things. So you're really measuring either differential pressure across a probe or probe array, or differential temperature from that probe or probe array. And that's the main two differences between pressure differential and thermal dispersion units. So your pressure differential units act like what's commonly called a pitot tube, where it's got different holes inside those probes, and it's measuring the overall system pressure as well as the velocity going across that probe. And it's using that to calculate the differential pressure between the actual airflow in the duct and the static pressure that's in that system. The thermal dispersion units are a little bit different in that they use an encapsulated thermistor, or some device that has a different resistance over a different temperature range, along with the heater. And that gets calibrated a specific way where you've got a known airflow through another calibrated orifice, and you can then figure out how much that airflow reduces that temperature, or how much electricity has to be put into that little heater next to the thermistor to create a constant temperature. And you can use that to figure out airflow. So if you know you've got no airflow and you have to supply X amount of voltage to this heating sensor to maintain a certain temperature, and then you know if you have to increase that voltage to maintain that temperature, you've got an increase in air, because that air is flowing across it and it's reducing that temperature. And you can do testing to be able to calibrate these sensors for that thermal dispersion unit. There's also some standalone pressure differential systems on top that we have available on top of damper and probe arrays. So the standalone pressure differential system works just like I had said before. It's got different probe openings, and there's basically a high pressure side and a low pressure side. And the differential pressure between that goes into a transducer that then measures how much that differential is and uses that with a known aspect ratio or duct size to be able to calculate that velocity as it's going. And then that system is going to send out an analog signal that can be sent back to, 2 to 10 volt analog signal typically, that would be sent back to the building management system that it then can use to determine a certain CFM of airflow going through the system. And that CFM can then be used to throttle a system. So if you have enough CFM, you can leave the fans running for however long it needs to have that air turn. If you don't have enough CFM, you can either open up a damper upstream of that or upstream or downstream of that fan to create more volume, or you can throttle the fans as well. There's a couple of different ways the building measurement system can adjust that. And it's typically going to be you're going to throttle the fans and you're going to adjust the damper at the same time to get that CFM, and typically open it up and increase that velocity to get more CFM or reduce it if you have enough CFM. So these thermal dispersion units that we have available now, really we only have available with a damper. We don't have a standalone unit for that. And that thermistor is heating that air locally and calculating that airflow, similar to the way the pressure differential transmitter is calculating the airflow through some type of pressure transducer. This is going to have, now these are a little bit different because you're not connecting, say, pneumatic tubes. It's all electrically done, but it's still going to be able to output that same 2 to 10 volts or 4 to 10 milliamp signal, 4 to 20 milliamp signal, excuse me. While it also typically has a little bit more advanced connection points, we do have some options available to connect to different, say, backnet type systems with some of the more advanced thermal dispersion units. Now, some of our pressure differential and damper combinations that we have right now use some pressure differential units with either a steel airfoil or an aluminum airfoil damper. We also have the same options available for the steel airfoil damper as well. So the naming convention pretty much mimics our control damper convention. So for the steel airfoil units, similar to the CD45, we use AM45 PD. So PD for pressure differential, AM for airflow measurement, and then 45 for the blade type. And that changes for that steel airfoil blade to TD for the thermal dispersion systems. We use the same aluminum airfoil blade nomenclature. So the AM51 PD for the pressure differential and 51 TD for the thermal dispersion. Now, one question I've actually gotten, which kind of makes sense when you're dealing with things from a traditional damper, volume control damper standpoint, is most volume control is done with opposed blade dampers. You can typically get a more accurate control of the volume with that. The problem that we've seen with testing some of these in-house is although the opposed blade dampers do control the air volume a little bit better, they also create more non-laminar flow when you're adjusting that. And in fact, most of these units are set up to where the airflow goes to the probes before it hits the damper. You're really going to get some you really want to set it up that way that you're not necessarily throttling your intake before the probes. You're actually throttling it after the probes. That works to create that laminar flow I was talking about. The non-laminar flow tends to force an increase of the length of your ductwork before the probes when you're using any type of damper, if you put it upstream of the measuring device. But oddly enough, if you use an opposed blade damper within a certain distance from the downstream of those probes, the turbulence from that opposed blade damper as it's closing actually starts to decrease the accuracy of those probes at a much closer distance than, say, a parallel blade damper. The opposed blade damper creates a little bit more turbulence upstream than the parallel blades do. So whenever we have a system that has the dampers and the probes together, the only way to get the damper installed that close to the probes without causing some inaccuracy in measurements is to use that parallel blade damper. So we really only have parallel blade dampers for the standalone units that have the damper and the probes together. Now, if you order those separately, you can certainly put an opposed blade damper upstream of our pressure differential offerings, but I typically recommend doing it downstream as well because it lets you put that damper significantly closer to the airflow measurement station. You're probably talking a difference of 5 duct diameters without some type of settling device or extruded aluminum screen that helps get laminar flow upstream of the damper, where you only have to keep that damper within, say, 1 duct diameter downstream of the airflow measurement probes. So that does help quite a bit when you're laying out the overall system. So when you're looking at different transmitters and you've got that standalone unit where you can split the damper and the pressure differential probes out, the transmitter we use is called the Scout differential DP for differential pressure, and it's a pretty simplistic device, but it's also a very cost-effective device compared to some of the other options on the market. We reduce the cost by removing, like, say, an LCD screen where you can actively see a CFM from it, and added a Bluetooth transducer. So there is a Scout app that you can download, and that'll show the CFM, and it pretty much makes for a very slimline, efficient, and cost-effective transducer. You don't have to take up a lot of sleeve area. So if you've got smaller airflow measurement probes, you can hook them up without like a large transducer with that screen. And honestly, what I've found with seeing a lot of these installed is the screen is okay when you're first installing them and going through the initial shakedown, but every time I've seen somebody either access it or look for that reading after the fact, they typically have to get into a ceiling or get into some access panel or get into a mechanical closet, which is not bad. But without, like, say, a Bluetooth or a wireless connection, you do have to put eyes on that unit. Whereas, Bluetooth connection, once you've linked that to, say, your cell phone and you've got building power to it, you can actually access that device quite a bit away. So the device can be in the ceiling, and if you want to do a spot check, you don't have to open up the ceiling or get into those mechanical closets. You can actually get relatively close to that transducer and still get a signal. Again, that'll have a 2 to 10 DC analog output, so you're not going to have connectivity to, say, more advanced systems like BACnet, and it'll have a 3% accuracy of reading, which is pretty standard. This is AMCA certified, so the Scout DP with the AM PD unit will actually be an AMCA certified airflow measurement station. Now, so the other options we have are from a company called Air Monitor, and those are all units that we have to sell with the damper attached. So these are great transducers. They are a bit costly, but do have kind of about the same inputs and outputs. They do have that screen, so you can get and you can look at the damper and get a CFM reading out of it, but they don't have that connectivity that some of the thermal dispersion units use, like, say, BACnet connectivity or a Bluetooth reading to a phone. Now, one other benefit to the thermal dispersion transmitters is they do have typical BACnet Modbus type connections, but you do have analog outputs as well. These are all going to take a 24-volt input and give you that analog output. Now, with the use of a resistor, you can change that from the 2 to 10 volt DC to 4 to 20 milliamp signal as well. That's pretty common. But these do have the additional options of that BACnet Modbus. They don't have that Bluetooth connectivity, though, so there's not going to be an app that you can use specifically for those. Now, we have some other cost-effective type options if you may be dealing with either like a DOAS system, so a dedicated outside air system, or if you're dealing with something that's not necessarily as complex, but you still want to maintain a certain level of, say, fresh air in a room, you can use a CO2 sensor. We partnered with Belimo to use some of their standalone CO2 sensors, and that do measure temperature and humidity. Now, they're duct sampling units and room sampling units. One question I get a lot of these is most people are used to, say, like fire smoke dampers with smoke dampers installed, or things where everything's kind of wired together. And that's a little counterintuitive when you're dealing with CO2 sensors. Typically, the CO2 sensors are going to be measuring either in a room, so you're actually in the occupancy, which is going to be probably a bit detached from where you want to install the damper to open and close to allow that outside air to come in as your fans kick on and turn off for that system. So you're typically not going to want these installed with the damper. Even when you're dealing with a dust sensor, you can certainly measure your CO2 at the damper, at the intake damper, but that typically isn't going to get you what you're looking for as far as a good CO2 reading. The duct CO2 sensors you typically want to install on the return. So you're going to want to measure, what air you're recirculating, which is typically going to be a different duct than your intake air duct. So most of the time, like these, they are a bit separate. And that's because the systems aren't as complex. You're not going to have bigger air handlers like you would on larger buildings where you're using, say, face and bypass dampers or other control dampers to recirculate that air or not. You might just be worried about opening and closing that, say, dedicated outside air system if you're dealing with, apartments or things like that that are maybe separated through different occupancies, or don't have that, say, common return and common exhaust, that you're in common intake that you're dealing with for a full building solution for your intake air. So these are going to be a little bit different. And that's actually one of the questions I get is, why wouldn't we have these sensors duct mounted? And typically you're not going to want to measure your CO2 levels anywhere but, say, inside the room, so for a wall sensor, or on your return air duct, which a lot of times these occupancies don't have a dedicated return air duct. It's a lot of times they're either going through a grill and a mechanical closet door, or a grill and a wall into a mechanical closet that's a little more free flowing, and it's recirculated that way. And you may be then opening a separate duct to increase that fresh air from the outside as your CO2 levels or even your humidity sensor levels increase. This is really just to kind of go through our offerings there. So one thing with this, it's got a CD25R damper for that CO2 damper. This is a pretty quick presentation. It's really just going over some of our models and what options are available, and some of the questions we've gotten so far, and really just go over the few models we have now. With that, I know this is new to Pottorff and new to a lot, so we wanted to give 15 minutes or so to make sure everybody's got time to bring up their questions and have a little bit room for discussion. So let me check the chat real quick,
Yeah, there's
just to
about
make sure.
questions in the chat. Oh, 4 questions in the chat.
All right. So I'll start with kind of how they came in. So who interpolates the calculation of converting the 2 to 10 volt signal to CFM? The BMS or the pressure sensor itself? So there's a couple of ways to do that. The pressure sensor itself will be able to have a CFM that gets displayed. So whether you're dealing with like the air monitor units that have a display, you'll see the CFM on that, and that's calculated locally at the unit. If you're dealing with the Scout DP, that's going to be calculated through the app. Now, both of these are going to send out that 2 to 10 volt signal that correlates to that CFM. So they're not going to send out a CFM. They're going to send out that 2 to 10 volt signal that then goes back to the BMS. Typically, it's not going to send out an actual pressure or a CFM. It's going to actually send that 2 to 10 volt signal that the BMS can then use to figure out your options. Are we pursuing any NIST qualifications? We're not pursuing any NIST qualifications right now. We do have some options available for NIST certifications from Air Monitor, and we can offer those, but we don't offer that with the Scout GP just yet. Do you offer thermal dispersion probes like Ruskin and Ebtron? We do offer thermal dispersion probes, but we do have to offer them with a damper at this point. We are working on seeing what we have to do to be able to sell the thermal dispersions like Ebtron or Ruskin standalone, not with a damper, but that's probably something we're going to have to take and develop over time because it's not something we have an option with Air Monitor right now. So it is something that we're looking into for just the probes alone. But right now, the only option we have is the probes and the parallel blade damper. Let's see. There are, let's see, one more question. Do we eventually plan to manufacture a round thermal dispersion unit that can be installed in inlet bell and integrated with a fan? That's certainly something we're looking into as well. We will most likely look at the rectangular devices initially before we develop, say, a rectangular thermal dispersion unit, but that's something we're definitely looking into. And then there's some questions about getting a copy of the presentation. We will have this recorded and we do plan to upload this to our YouTube channel. We can get PDF copies of the presentation if there's anything if anyone wants that as well, or it's anything that people want to look at.
Where do you have a data sheet on the Scout DP?
Yeah, we've got, so the Scout DP, the catalog sheet for the overall unit, we have kind of covering both. We don't sell the Scout DP as a standalone. We pretty much just sell it as this unit now. But so it's kind of combination of the IOM and everything else. Are you looking for just the transducer or the overall system?
My initial look, I wasn't able to find it at all, so I was just kind of curious about it.
Sure.
I even searched Scout and it didn't come up. So
Yeah, it's just
located.
gonna be, it won't have its own standalone sheet. It'll be in conjunction with the AMPD sheets. So we've got like the third page of the installation manual covers that, and then if there's anything covering, say, the overall size of the unit or anything like that, or how it will be mounted, we show that along with the AMCA certification with the probes we used. Now, we wouldn't be able to sell just the Scout DP as a standalone product with any certification because the certification takes into account the probes we tested with as well as the transmitter. But we can look at potentially selling those independently. There's just going to be, it's going to be tough because you typically have to have the probes and the transmitter ordered together. So that's kind of why we've got it split up that way. And I can show you what we're looking at. Let me switch over quickly. I can share the website. So here's our installation manual, and the third page, excuse me, is the catalog sheet, excuse me. Here's kind of the physical unit itself, and then on the installation, the third page this is pretty much, I think this is kind of what you're looking for the Scout, right? So it's got your pressure ranges, your inputs, your outputs, operating temperatures,
Yeah,
and
that's fine. My mouse died, so sorry. I'm fumbling around with my fingers here.
We can send you a copy of this as well.
Well, and the sheet you showed with it on the end of the shaft and all, or on the end of the damper, it was nice looking. So I was trying to find that too. But
yeah, if there's specific images you'd like to look at or use, we can get those to you as well. Typically there's no field calibration that needs to be done as long as we've had, the way the ordering works is there's a CFM value we've got the size of the ductwork. So we can factory calibrate it to those sizes. There typically doesn't need to be any field calibration unless there's been some type of change or you're using it in different ductwork, because there'd have to be a different K factor for the pressure differentials, or there's a little bit of programming for the thermal dispersions, but the thermal dispersions will come factory calibrated. So really, it can go through, there's going to be a procedure for the unit to self-calibrate if you're seeing errors in the field, but typically that's not needed. The only time I've seen that needed is if there was something either wrong with the unit or something changed along the way. But typically, because we've got that for the ordering process, there'll be a CFM, a system CFM that we use, or a feet per minute, and then the duct size can use to calibrate it. So there's really no field calibration needed for these. They're typically set up from the factory that way. Now, if there are problems as it's set up, you can certainly contact us for technical support. We've had to go out to job sites to look at things for certain jobs, and there's some things we were able to walk through on the phone. Now, if that kind of diagnostic runs through and there is some failures at that point, there may be something might have happened to the unit, and we'd have to work at some replacements there. But typically, they're relatively plug and play for these. Not really a lot of field calibrations there. The pressure differential units we have aren't as generic as, say, a controls contractor would have, that they would have to use a calculation to set up a K factor based on varying duct sizes and velocities. So since those are all set at point of order, it's typically set up from the factory that way. These are all great questions, by the way. Any other questions? People can feel free to voice them now. We can throw them in chat.
I think there's a question. How
Yeah, how
often
often do these need to be calibrated for drift? Typically, these don't really need to be recalibrated for drift all that often. There's typically, if you are getting some odd readings or things like that, they can be recalibrated, but typically these don't really need a ton of recalibration for a certain amount of time. At least most of these we're outsourcing from other manufacturers. We don't build these in-house, and we don't have any current requirements for, say, recalibrating annually, semi-annually for drift. Pretty much once they're set up, they're pretty good to go, as long as there's no massive change in the duct size, which shouldn't happen, or the probes are damaged or clogged up in any way. Typically, that's not necessary. Yeah, any other questions? We've got a few minutes left. I know we started a little late. The velocity ranges for the PD. So it's going to be a little bit different for the two different devices. The AMPD, so the standalone unit, our velocity range is going to be typically it's got to have a max of about 2,000 feet per minute, and the pressure, and it's typically gonna start, you're gonna get some pretty inaccurate readings below 200 feet per minute. Now you can use it at those lower ranges, but they really don't work that well for those. The air monitor options available do have lower pressure and lower velocity probes. So those we do have a little bit wider of a size range, but you're probably looking at something that's a little bit outside what kind of your standard velocities are doing. So with those, we can get down to about 300 feet per minute as well. And there's going to be, once you start getting above the 2,000 to 4,000 range, things do they don't really work quite as accurately. You're going to get to the end of those ranges. So for that, I typically don't recommend setting up for over 2,000 feet per minute for a lot of those. And when you get below 500 or 600 feet per minute, we do have to go to special construction for the airflow measuring equipment from air monitors. So whether that's the Veltron 2500 or and the probes associated with that. But typically, when you're getting that low, even with the thermal dispersion units, your accuracy is going to suffer quite a bit. And we can get you some. I know they're not on the submittal sheets right now. We can look into that. For the AMPD, are pretty much anything below, once you start getting below 300 feet per minute, your accuracy is going to get worse. We've got some accuracy data for that lower level up to about 2,000 feet per minute. For the units we do have, so it's not going to be on, say, the first page. It'll be in the AMC numbers so typically 300 to 2,000 CFM is where you're going to get your accuracy. You can use it at lower velocities, but anything below that 300, your accuracy is going to start suffering significantly. And it's going to be pretty similar for any air monitor units we have as well. And if anybody has any other questions or anything that they want to bring up, feel free to email us. You can email me directly, jcarlin, so JCARLIN at Pottorff, POTTORFF.com. Or reach out to our customer service group or info@pottorff.com if that works. We can certainly answer any additional questions that may come up after the fact. Thanks for your time. Feel free to reach out again, and we'll go from there.